Hello everyone. The title of this video is Graphing Polynomial Functions. So every example I'm going to be doing in this video is taken directly from a free online textbook at openstacks.org, and I'm in their Algebra and Trigonometry text, section 5.3, called Graphs of Polynomial Functions, and I'm under the heading Graphing Polynomial Functions. And each example will either be an example from the reading, or one of the try it problems from the reading, or one of the exercises at the end of the section related to this particular objective. Alright, so I'm just going to go over this how-to box here because this is what I'm going to do for you in each of the examples I've got. It's how to, given a polynomial function, sketch the graph. And this is pretty much putting together all the little bits and pieces of the previous videos from section 5.3 and also even 5.1 and 5.2 of this text. Just kind of putting it all together to make one complete graph. Alright, so first we're going to find the intercepts, or the x-intercepts, the y-intercept. Then two, I usually don't do this, but again I'll do it for you here because it's mentioned. Check for symmetry. Right, is it an even function? Does it have y-axis symmetry? Is it an odd function? Right, does it have origin symmetry or neither? Right, it might have neither symmetry, but that'll give you, if you know it has a certain kind of symmetry, then it better look that way when you graph it. Right. Number three, use the multiplicities of the zeros, right, the x-intercepts, to determine the behavior of the polynomial at the x-intercepts. Remember, if a zero has odd multiplicity, the graph will cross the x-axis there. If it has even multiplicity, the graph will hit the x-axis but then bounce off the x-axis, if you want to call it that. And the higher the multiplicity, the flatter the graph is near that zero. Then determine the end behavior, right, by examining the leading term. What's happening on the far right, the far left, right, as x goes to infinity or negative infinity. Then use the end behavior and the behavior at the intercepts, at the zeros, to sketch a graph. And then make sure that the number of turning points does not exceed one less than the degree of the polynomial. Remember, if it's a degree n polynomial, the graph will have no more than n minus 1 turning points. Right? And a turning point was where the graph went from increasing to decreasing or decreasing to increasing, tops of hills, bottoms of valleys. And then I will do this, I know it says optional, but use technology to check the graph. So I'll graph it by hand as best I can. And then I'm going to go to that free online graphing calculator at desmos.com and just compare my graph to the graph I'll get there. Right? Or you use a graphing calculator that you have, it doesn't matter. Right? Okay, so again, I'm going to follow these steps as we go through each example. Alright, so the first example I have, again, we have the same instructions, just sketch a graph of the polynomial function. I have f of x equals, 1/4 times x times the quantity x minus 1 to the 4th power times x plus 3 to the 3rd power. Right. So the first thing was the intercepts. Right. The intercepts. Right. So the y-intercept is simple enough, right? You just plug in 0 for x. What's f of 0? Now I'm hoping it's obvious here, but there's a factor of just x. So if I replace x with 0, you're going to have 0 times whatever, and the whole thing will be 0. Alright, so the origin, right, 0, 0, is the y-intercept. And notice that that is also an x-intercept, right? It's on the x-axis as well. But let's find those. Find the x-intercepts. So this is where you're solving this equation. When is f of x, when is the output equal to 0? All right, so when is 1/4 times x minus 1 to the 4th times x plus 3 to the 3rd, when's that equal to 0? Well, the nice thing is this particular function, this polynomial is already factored for us. And if you recall, the zero product property, a product can only be 0 if one of the factors is 0. So either 1/4 is 0, but that's not happening. 1/4 is not 0. But if x is 0, that'll happen. Or if x minus 1 is 0, this'll be true. Now I'm not writing x minus 1 to the 4th power because it's just the same factor 4 times, right? It's just x minus 1. Same thing for the x plus 3. That's a factor 3 times. Those will be the multiplicities of the zeros, right? We'll talk about multiplicities later. So x plus 3 could also be 0, and this should be true. And then we get, x equals 0, x equals 1, and x equals negative 3. Right? These are, what are called the zeros of the function, right? They're where the graph will cross the x-axis. And so we have our x-intercepts, input 0, output 0, input 1, output 0, and input negative 3, output 0, right? So here's the x-intercepts, the y-intercept, which is the same as one of the x-intercepts. Okay, and then just because we're going to be using it later, I'm also going to talk about the multiplicities of these zeros. Right? So remember, the multiplicity of a 0 is just how many times does that factor that it makes 0 show up. Right? X equals 0, there's x to the 1st power. So that has a multiplicity of 1. For x equals 1, the factor of x minus 1 was a factor 4 times. It's x minus 1 to the 4th, so it has a multiplicity of 4. And x equals negative 3, right? The factor x plus 3 is a factor 3 times, right? It's to the 3rd power, so it has a multiplicity of 3. Okay. So we have two zeros with an odd multiplicity. So the graph will cross over the x-axis at these zeros, and one with an even multiplicity. Right. But we'll get to that in a second, because the next thing they wanted to talk about after finding the intercepts was symmetry. Right, check for symmetry. If there is any. So for here, I'm just replacing x with negative x and seeing what happens. What's f of negative x? So replace all the x's with the opposite of x, and again, just see what happens. This would be 1/4 times negative x times, negative x minus 1 to the 4th power times negative x plus 3 to the 3rd power. And then you're asking, is f of negative x equal to the original? Or is f of negative x equal to the opposite of the original? Because if one of these things happens, it's going to be either even or odd. And if the answer to both these questions is no, then it has neither of those symmetries, right? It doesn't have y-axis symmetry or origin symmetry. All right, so one thing I'm going to do here is pull out the negatives here. So we'll have a negative pull out of here. Now if you pull out 1/4 times x, pull the negatives out front. Now if I pull a negative and 1 out of this factor, it'll be x plus 1 to the 4th. Right, pulling a negative 1. And then negative 1 to the 4th power would be positive 1, so that's gone. And then pulling a negative 1 out of this factor would be x minus 3 to the third. And negative 1 to the third is negative 1. Times the negative 1 from here makes it positively coefficient. So here's f of negative x. And then you got to ask yourself, is this the same as this? Absolutely not, right? This has factors. This has zeros at 1 and negative 3. This would have zeros at negative 1 and positive 3. So totally different. So the answer to that question is no. So the function's not even. All right, f is not even. It doesn't have y-axis symmetry. And again, is this equal to the opposite of this? Absolutely not. The opposite of this, you just throw a negative in front. It would still have zeros at 1 and negative 3, whereas this has zeros at negative 1 and positive 3, right? The opposite of this is a totally different function than this f of negative x here. So again, the answer is no. So f is not odd either. All right, so that means f, is neither even nor odd. There is no symmetry about the y-axis. There is no symmetry about the origin. Okay? So, done with that check. All right, so now we're going back and talking about the multiplicities, right? Step 3 was use the multiplicities to determine the behavior of the polynomial at these x-intercepts. So once again, this is an odd multiplicity for x equals 0, so the graph will cross the x-axis, and it's going to cross the x-axis like a degree 1 polynomial, like a line straight through. Whereas this with the x equals negative 3, 0, with a multiplicity of 3, the graph will also cross the x-axis here, but like a cubic. Right? It's going to cross straight through at x equals 0, but it's going to cross more like a cubic, like a degree 3 polynomial at x equals negative 3. And then for x equals 1, there's an even multiplicity. The graph is going to bounce off the x-axis here. But not like a parabola. It's going to be a little flatter because, this will bounce like a degree 4 polynomial. So like it'll touch and then come back up. It's like a parabola but wider and flatter at the bottom. Because, it's not a multiplicity of 2, it's a multiplicity of 4. And I mentioned this earlier, right? The higher the multiplicity, the flatter the graph will be near that 0. Right. Okay, so I've described what's going to happen, and we'll make this stuff happen when I go and graph the thing later. All right, now step 4 is determine the end behavior. I've talked about this all of these things in previous videos, but end behavior is just you only need to identify the lead term. What's the leading term of this? Now you can multiply the whole thing out if you wish. Take all that time. That would take a long time here because what's x minus 1 to the 4th power? What's x plus 3 to the 3rd power? And then you multiply those, and then you distribute the 1/4 x. That would take too long. And I've mentioned this before. If you want the lead term, just multiply the lead term of each factor. So you have 1/4 times x, and then times x to the 4th times x to the 3rd. So really it's x to the 8th. Right, because you have x to the 1st here, then x to the 4th, x to the 3rd. Right? If you multiplied the lead term of every single factor. So this is an even degree, right? The degree of this polynomial is 8. So even degree. And the lead coefficient is, positive 1/4. Right? So putting these together, the graph's going to be doing this. Here's the xy plane. The graph, with an even degree, positive lead coefficient, will be going up on the left end and up on the right end. Now, if you want to describe this a little more further, you say as x goes to infinity, all right, this is going to the right end, the value of the function is going up, which will be going to infinity along the y-axis, right? F of x is going to infinity. That's the right end behavior. Then to describe the left end behavior, you say as x goes to negative infinity, right? What happens as you go to the left? Well, the value of the function is still going up. So f of x is also going to positive infinity over there. Right, so there's the end behavior. Right, so that should be happening when we do our drawing later. All right, one other thing, talking about turning points. I mean, we'll make the graph. We'll actually sketch the graph, but after that, they were talking about turning points. If this is a degree 8 polynomial, the graph can have at most should have at most 7 turning points. All right, so if I draw this thing and it has more than 7 turning points, I did something wrong. All right, this is a degree 8 polynomial function, so it should have no more than 7 turning points. All right, so now let's actually sketch this thing. Going back through the steps again. Now this is going to be a rough hand drawing here, but just make a. Now if you have graph paper, maybe that'll be nice, but I'm just going to do it here on this solid sheet. So x and y axes. We had the intercepts. Right, the intercepts we saw were 0, 0, 1, 0, and negative 3, 0. So 0, 0, say there's 1, 1, 0, and over here, negative 3, 0. Again, I'm going very rough, just putting numbers where they in the correct relation to each other. We know the end behavior, right? Should be going up to the left and up to the right somehow. All right, when we're done. And then the behavior at the intercepts, right? We said it was going to cross at x equals negative 3. It's going to cross like a cubic. Right? So we're going to start up here, come down, and it's going to cross at x equals negative 3 like a cubic, right? Not straight through, but more curvy. All right, then it's got to turn around eventually, right? So there's got to be a turning point here somewhere to get back to 0, 0. And then at x equals 0, it's going to cross straight through, right? The multiplicity at 0 was 1. So it's going to come down here, and then it's got to turn at some point. Again, I don't know how low it's going, but there's got to be a turning point somewhere where it goes from decreasing to increasing. And then it's going to cross at x equals 0, cross straight through, like a line. And then once again, it's got to turn at some point to get back down to 1, 0. All right, but then at 1, 0, remember, it's going to hit and be like flat, flatter and almost like and bounce off, right? Remember, we said x equals 1, the multiplicity was 4. It's going to bounce off the x-axis, not cross over, and be a little flatter because the multiplicity is higher. So maybe something like this, and bounce off, and then continue up, so it actually ends up going up to the right. So up to the left, up to the right, crossing at negative 3 like a cubic, crossing at 0 like a line, and then bouncing off the x-axis at x equals 1, but a little flatter because the multiplicity is higher. So there's a rough sketch, and let's count the turning points. Right? There's in my drawing here, there may be more. It might be a little wavier in some places. I don't know. Okay, if you want to know exactly how many turning points something's going to have before drawing it, you're going to have to get into a calculus course. All right. But that's beyond the scope of this video right now. So there's a turning point in my drawing. And here's another one. And here's another one, right? Turning point, turning point, turning point, right where it goes, basically again, bottoms of valleys, tops of hills. So we got 3 turning points, which is okay. Right? So my drawing isn't impossible. That's okay. Remember, it was a degree 8, so it can't have more than 7 turning points, which our drawing doesn't. Now, that last option was, optional, right? The last step. Go to a calculator, go to technology, and let's see how our graph compares to a better looking computer generated graph, right? So back here, back to that Desmos website, right? Desmos.com. Oh, sorry, that's from a previous video. I'm going to enter the function we were given, right? F of x equals 1/4 times x times the quantity x minus 1 to the 4th power, then times the quantity x plus 3 to the 3rd power. And look at that. See how it's going up to the left, up to the right. It crosses x equals -3 like a cubic, right? It doesn't come straight through it, it kind of curves into it like we said. And then it turns at some point. Now it's turning way deeper than I drew. Way further down at like -50 here. It turns here, but there is one turning point. All right, one turning point. And then it crosses at x equals 0. All right, we said that. But see how it crosses straight through like a line, because multiplicity was 1. Then here's a second turning point between x equals 0 and 1. And then see how it's at x equals 1, it bounces off the x-axis, right? It doesn't cross it. And you see how it's like a flatter, it's not like a parabola exactly, a little wider, right? Because the multiplicity was higher, it was 4. And then it goes up to the right forever, right? So the end behavior is correct. Even our number of turning points was correct, right? There were 3 turning points. Just this turning point between -3 and 0 was way deeper, way lower than I thought, than I drew. But the graph we drew is pretty good rough version of this graph. And we were correct in the number of turning points and all that, the end behavior, the intercepts, how the graph is crossing or bouncing off at the intercepts. So I'm happy with it. All right. Great. So yeah, that's all we're doing, right, is making these rough sketches of these graphs. All right. Okay, so next example, doing the same stuff, but I'll go a little faster. Right, because some things should be a little more obvious than others. So example 2, we're given a function f of x equals x plus 3 squared times x minus 2. Once again, it's in a nice factored form for us. So the intercepts should be simple. Now the y-intercept, if you plug in 0 for x, you're going to have 0 plus 3 squared, that's 9, times 0 minus 2. So you'd have 9 times -2, be -18. So there's the y-intercept. Then the zeros, and I'll also list their multiplicities in a little chart here. X plus 3 is a factor twice, right? So x equals -3 will be a 0, right? Or just -3. And I'll make that factor 0 and give you an output of 0, right? And then there are again 2 of those factors, right? So the multiplicity is 2, meaning the graph will bounce off the x-axis here. And it's going to be like a parabola, right? Like a degree 2 polynomial, right? Like this or like that, right? Depending on which way we're coming from. Okay. And then the other 0, the other x-intercept, is going to be at x equals 2, or you can just write 2. And there's only one factor of that, right? So the multiplicity is 1. and the graph, with an odd multiplicity, the graph is going to cross over, or just cross the x-axis. And because the multiplicity is 1, it's going to cross just like a straight line. All right. Okay. So the intercepts are 0, -18, then we have -3, 0, and 2, 0. Right, those are the points that'll be on the x-axis. All right, now for the symmetry stuff, f of -x would be, -x plus 3 to the second times -x minus 2. And if I factor a -1 out of this, -1 squared is +1, so you'll just be left with x minus 3 squared. And then pull a -1 out of this, I'll put a negative out front, and then you'll have times x plus 2. And this has zeros at 3 and -2, where this has zeros at -3 and +2, so they're not the same. This is not the same as the original. So, the graph's not even. Doesn't have y-axis symmetry. And also, if I threw a -1 in front of this, took the opposite of this, they're not the same either. They have different zeros again, so it's not the same as the opposite of f of x either. So the graph's not odd, the function's not odd either, right? So it doesn't have y-axis symmetry, doesn't have origin symmetry. Okay, the lead term would be x cubed. And if you were to take x times x times x, right, just multiply the lead terms from each factor. So it's odd degree, right, degree 3, and a positive lead coefficient, right, +1. Right, so the end behavior, which I won't write out a description of, I'll just draw it. Odd degree, positive lead coefficient, the function should be going down on the left end and up on the right end. Okay, and since it's degree 3, the graph should have no more, or at most no more than 2 turning points if it's degree 3. All right, so again, if I draw something and it has 3 turning points in it or something, then I know I did something wrong. All right, so again, off to the side here, a very rough sketch. So here's x-axis, y-axis. 0, -18 is the y-intercept. -3, 0 is one of the x-intercepts. +2, 0 is another x-intercept. And I know the graph has to be starting from down here, right, and then ending up going up to the right. So starting from down here, I have to increase until we get to -3, 0, and then at -3, 0, the graph that we said is going to bounce off the x-axis like a parabola, like a degree 2. Right? The multiplicity was 2, so something like that. All right, then it's got to come down and eventually hit, this y-intercept, and then it's got to turn at some point to get back to 2, 0. So I don't know if that's the turning point or not. It may be. All right, but it might also not be. Again, finding exactly where the turning points are is a calculus thing. All right, and I'm not teaching calculus in this video. We're just drawing very rough sketches of polynomial functions. All right, and then it's got to turn at some point, come back up and hit at x equals 2. Now at x equals 2, it's got to cross, it's got an odd multiplicity, and it's crossing like a line, and then continue on, to end up going up to the right. So something like this. And if you count the turning points, right, there's one turning point, and there's got to be two. There are 2 turning points in my drawing, which is fine, right? Can't have more than 2 turning points though. Now let's look at an actual graph and see how it compares to the graph I just drew. All right, so this function we were given, f of x equals, we have the quantity x plus 3 squared times the quantity x minus 2, and yeah. Now, see that it's got left end, the left end it's going down, the right end it's going up, end behavior is good. See there's 3, 0, and see how it's bouncing off like a parabola at the x-axis. There's 2, 0, where it's crossing straight through, just like in my drawing. Here's the y-intercept, 0, negative 18. I know, look at that, the turning point is right after it, kind of like in my drawing. That turning point of, 1/3, negative 18.5, whatever. But it's got 2 turning points, down to the left, up to the right, bouncing off x equals negative 3, crossing over at x equals 2. Looks almost exactly the same as the drawing I made. And so this is, again, a very good rough sketch of that function. Great. And again, no y-axis symmetry, no origin symmetry. All right, next example. I got just 2 more of these. All right, so again, it's nice and factored for us. I think all of these are. All right, just to make it easy on us finding the intercepts and whatnot. F of x equals, x minus 1 cubed times x plus 3 squared. So again, I'll start with the intercepts. Now the y-intercept, you plug in 0 for x. This would be negative 1 cubed, which would be negative 1, times, and then this would be 3 squared, which would be 9. Negative 1 times 9 would be negative 9. All right, so the y-intercept is at the point 0, negative 9. And now for the x-intercepts, or the zeros, or the roots, all those words kind of mean the same thing. And I'll also list their multiplicities, and we'll talk about how the graph is going to, behave near these zeros. Now x minus 1 is a factor, right? So x equals 1 is a 0, or just 1. And that's a factor 3 times, right? So the multiplicity is 3. Meaning the graph will cross over the x-axis at x equals 1, but it's not going to cross straight over. It's going to cross over, like a cubic, like one of these curves, right? Like a degree 3, multiplicity 3. All right, then x plus 3 is a factor, so x equals negative 3 would be a 0. All right, make that factor 0, but there are 2 of those, right? So it's a multiplicity of 2. Meaning that at this 0, at this x-intercept, the graph is going to bounce off the x-axis. And it's a degree 2, it's a multiplicity 2, so it's going to be like a parabola, right? Okay, and then if you want to actually list the other intercepts, right, 1, 0, and negative 3, 0 are the points of this graph on the x-axis. Cool. Alright, then off to the side here, the symmetry part. Again, usually I don't do this, but they asked us to in this, and they're talking about symmetry in the text, so I'll do it. Replace all the x's with negative x. So it'll be negative x minus 1 cubed times, and then negative x plus 3 squared, and then if I factor a negative 1 out of each of these, now negative 1 to the third is negative 1. But then if you pull out a negative 1 from these, you got x plus 1, and you still have 3 of those factors. And then pulling a negative 1 out of this factor. Now negative 1 squared is positive 1, so that doesn't change anything. You still have this minus from earlier. And then these factors become x minus 3, and you still have 2 of those. Alright, so once again, this is clearly not the same as the original. Not the same as f of x, so not even. Again. And it's not the same as the opposite of the original either. They have totally different intercepts. These have, this and its opposite would still have intercepts, would still have zeros at 1 and negative 3. This has zeros at negative 1 and positive 3. Totally different. So not odd either. So once again, and you're going to see that with all these examples actually. Again, part of the reason why I usually skip this part, because I don't see too often problems like this where there is symmetry of some kind. So not even, not odd, no y-axis symmetry, no origin symmetry. Let's keep that off to the side. All right. Okay, then for the end behavior, right? What's the lead term? Now the leading term would be x 3 times x squared, multiply those, that's x to the 5th. So once again we have odd degree, right, degree 5, and once again we have a positive lead coefficient. I'll just say positive lead. Alright, so if you're talking end behavior, just like the last example, it's going to be going down on the left end, up on the right end. And it's a degree 5, so it has to have at most, right, can have no more than 4 turning points. Right, so just so I know, if I draw this picture and I have more than 4 turning points, I did something wrong. Alright, so let's do a rough sketch of it over here. Again, the y-intercept is at 0, -9. X-intercepts are at 1, 0, and -3, 0. And I got to start from the left end's got to go down to the left, so I'm starting from down here, coming up to -3. But then at -3, see, at x equals -3, we said it's bouncing off. So it's almost exactly like the last one, where it's touching and then bouncing off like a parabola. Then it's got to eventually come down and hit at 0, -9 here. I'll just say that's the turning point. It probably isn't, but I'll have it turn there because it's got to turn there and eventually come up to hit 1, 0. But it's not crossing straight through at x equals 1. It's crossing like a cubic. All right, so getting a little curvier, so like this maybe. All right. So not crossing more like a cubic there, and then continuing on up, right, to keep the end behavior the same. Down on the left, up on the right. Bouncing off at -3, crossing over like a degree 3, like a cubic at x equals 1. And you got 2 turning points here, which is not more than 4 turning points. So my drawing is okay. Again, I don't know exactly where the turning points is. That's a calculus thing. If you want to find by hand exactly where the turning points are, you're going to need to go into a Calculus 1 course. Okay, so let's see how our graph compares to the real graph. So the function we're given, f of x equals, the quantity x minus 1 to the 3rd power times the quantity x plus 3 to the 2nd power. All right. So again, the end behavior is hopefully the same, right? The same as we've had, down to the left, up to the right. You see the intercepts, there's -3, 0, and the graph is bouncing off the x-axis there like a parabola. See, there's 1, 0. And you see how the graph is crossing over like a cubic, like a degree 3. And then you got the y-intercept at 0, -9, right, which is not the turning point. All right, so my drawing's a little off with that. The turning point, that other turning point was down here at like, -1.4 or -35 something. All right, but everything else is the same. Everything else is correct. The intercepts are correct. How the graph behaves near the intercepts is correct. The end behavior is correct. The y-intercept is correct, right? Everything else is correct about this, and even the number of turning points is correct that I have drawn. So my rough sketch, isn't too terrible. It's not perfect, but again, these are rough sketches that you're doing at first glance for these polynomial functions. Great, and let's do this just one more time. I got just one more here. Again, it's in factored form. Later in a later section in this chapter, we're going to do the same stuff, but the polynomial won't be factored. We'll have to factor it ourselves. But once you do factor it yourself, it'll be just as easy as these to make a rough sketch of the polynomial function. Alright, so the intercepts. Now again, if x were 0, y would be 0 because there's a factor of just x. Right? And so that's actually one of the zeros as well. And I'll just put mult this time for multiplicities. So yeah, x equals 0 is a 0. X equals 1 is a 0, because x minus 1 is a factor. And x equals -3 is a 0, because x plus 3 is a factor. And each of these has a multiplicity of 1, right? X to the first, x minus 1 to the first, x plus 3 to the first. So for all three of these zeros, the graph is going to cross the x-axis. And it's going to cross like a degree 1, like a line. Just straight through, or straight through, like that. But it's going to cross the x-axis like a straight line at these intercepts. Okay, checking the symmetry. Once again, I can already see that this has no y-axis symmetry or origin symmetry. But you can verify it by, again, looking at f of negative x. That's, negative 2 times negative x times negative x minus 1 times negative x plus 3. And if you factor out all the negatives here, there's, 2 negatives make a positive, 2 negatives make a positive, so it ends up being positive 2 times x plus 1 times x minus 3. And again, this is not the same as the original. There's totally different intercepts. I mean, they both have an intercept at 0, but this has intercepts at negative 1 and positive 3, whereas this one has intercepts at 1 and negative 3, right? So not the same as f, or the opposite of f either, because again, the opposite of f would also have intercepts at 0, 1, and negative 3. This has intercepts at 0, negative 1, and positive 3, totally different. So it's not even, not odd, again. Again, I usually skip this part, but no y-axis symmetry, no origin symmetry, once again. All right, now for the end behavior, we need to determine the lead term, which would be negative 2x times x times x, so negative 2x cubed. All right, so we have odd degree. All right, it's degree 3. But this time we have a negative lead coefficient. I'll just put negative lead. All right, so putting those together, right, that just, the graph would have to be going up to the left end and down on the right end. And with a degree of 3, can have at most 2 turning points. So again, if I draw this thing and I have more than 2 turning points, then I should know I did something wrong. Alright, so let's make a rough sketch. Here's the xy plane. The intercepts, I didn't write all the intercepts in. We got 0, 0, 1, 0, and negative 3, 0. All right, so 0, 0, 1, 0, and negative 3, 0. And it's got to start from up here, right? We're going up to the left, and then it's going to cross, cross at negative 3, but like a straight line, right? Cross straight through. Then it's got to turn at some point to get back to 0, 0, so there's a turning point. And again, it's going to cross straight through. The multiplicity is 1. And then it's got to turn again at some point. There's another turning point to come back at 1 and cross straight through. And then continue down forever, right? It's going to go up to the left end, down on the right end. You got 2 turning points, which it should have no more than 2 turning points, so we're so far so good. And it's crossing each of the intercepts like a line, right? Crossing straight through at each of the x-intercepts because the multiplicity was 1. All right, and again, these turning points, I don't know if this goes lower than this or this goes higher than this. All I know is that there should be 2 of them. Once again, if you want to figure out by hand exactly where these turning points are, you're going to need calculus. All right. Okay, so let's take a look at this and see how it compares to my graph. So once again, back on the Desmos site, just entering the function they gave us, f of x equals negative 2x times the quantity x minus 1 times the quantity x plus 3. And yeah, you see how it's up to the left, down to the right. The end behavior is correct. The intercepts are all correct, right? The intercepts at negative 3, 0, and 1. And you see how the graph is crossing straight through at all these. And there are 2 turning points, just like in my picture. Now again, this probably dips lower than I had in my picture, and this isn't as high as I had in my picture, but still there are these two turning points between these intercepts. Great, so it doesn't look half bad, my rough sketch. I got a rough idea as to how the real graph looks, right? And that's it. These 4 examples I think are enough to, maybe just the first example was enough, but to get you an idea as to how to make a quick sketch of a polynomial function, especially if it's in factored form. Right? All these examples were in factored form already, so that made it a little easier. As I mentioned earlier, later in the text we're going to see examples that are not factored and that we have to factor ourselves. But once you have factored them, it should be just as easy as I've had here. Alright, and I'm hoping that watching me go through these 4 examples helps you in some way when you're asked to make a quick sketch or rough sketch of a polynomial function on your own. And thank you very much for watching.